Hey guys, my name is Mauricio Crispim, and in response to requests in today's video, we will show how to calculate the load loss in singularities along a network of air conditioning ducts. Don't forget to ask you, if you like it, give it a like, subscribe to the channel, and we will try to continue bringing you quality content. The uniqueness as shown in the images back here, just those excerpts from the doctor, we almost found curves, knees, transitions, ramifications, collars, etc. Each of these has a specific load coefficient according to its geometry and proportions between measurements. The Ashway and Macrix databases, which are the two main associations that deal with the topic, define more than 200 geometries to bring uniqueness. Unfortunately, the database that these associations make available in their manuals and also in project software are not distributed free of charge, and in this tutorial we will deal with the main ones with their average coefficients. However, I guarantee that the singularities presented here will be sufficient for most projects that you may encounter in your profession. In our calculation, once again, we will use the Duct Sizer software, which is made available free of charge by the manufacturer Duct. In the previous video, we've already showed how to download this application. Let's look at our calculations in practice. So in our exercise, we will calculate the load losses in the most common typical singularities existing in a pipeline network. And what are they? So we have the first one, which is the smooth curve with a long radius. Then we have the straight knee, where the load loss will vary according to the angle from 0 to 90 degrees. Then the straight knee of 90 degrees with vanes that decrease a lot of pressure loss. Then the branching with a smooth curve with a long radius curve. Then the T branching from a rectangular section to a circular section. This is a very typical connection when we are dealing with rectangular duct branching to flexible duct, and then lastly, an entire branch from a rectangular section to another rectangular section. For our calculations, we will use the application that we already showed how to download in the other video, which is Duct Sizer, provided by Daiquim Makui. It's a small, compact program that you download quickly, but it's very useful for your calculations because we can consider it to be quite accurate. So it's a small and useful program because it's very precise. So first thing, let's change the units, the metric units, which makes it easier for us to work. And here, I will consider that we are going to work with a duct. This one, I will consider that I have a flow rate of 2,000 cubic meters per hour. 2,000 cubic meters per hour. Our program uses it in liters per second, so I have to dividing by 3.6, I will have my flow rate in liters per second. So 2,000, I will have 555 liters per second. Okay, so let's go here in my program in the Duct Sizer. I will put 555 liters per second. For the load loss golden tip, you should use 0.5 pascals per meter.
Done.
Give it a speed. The speed is okay, 4.13 meters per second to have this load loss. Let's put in a duct of 50 centimeters, 500 millimeters. A duct of 50 centimeters. To give this pressure loss, it should have a height of 300 millimeters. I'm going to increase it a little here to make a duct of 550, and then the duct is exactly 55 centimeter by 27.5 centimeters. So it was a duct of 55 times 27.5. The average pressure loss coefficient in a long radius curve is 0.25, but this average coefficient I also have to multiply by the angle factor, my angle factor. It can say correct up to 180 degrees. It would be a complete turnitus, a rare thing of Vengeron normally. The color will be minty degrees, 45 degrees, something like that, because we're using our program here, because I will need very important data, which is the dynamic pressure, so it informs that the pressure due to the speed, that is 9.75. So this one here is my PV. For this duct, it is 9.75 pascals. 9.75 pascals, so I can convert it to millimeters of water column, multiply by 0.12. So my pressure loss, for example, if my angle here were 45 degrees, I would have a loss here. It will be equal to 9.75 pascals dynamic pressure times 0.25, which is the coefficient times my angular factor, which I'm considering is 45 degrees, which will give 0 times 0.60. This here gives me 9.75, bond 25, 6 times a loss of 1.46 pascals. Gives me a loss of 1.46 pascals, converting to millimeters, and gives a pressure loss of 1.46 times 0.12, 1.46 x 0.12, which will give 0.18 column D water. Okay, so let's move on to another very common singularity, which is the straight knee.
Done.
So straight knee, I will consider the 90-degree knee. So again, my duct continues with the same section, a section of 55 by 27.5. So I will put here that my loss will be 9.70, which the dynamic pressure times the average C4 90 degrees, which is 1.1, which will give here 9.75, 1 point times 10.73 pascals, or multiplying by 0.12, which will give 1.29 millimeters of water column. Let's go in straight knee. It looks like I have a much greater pressure loss, for example, than a 45-degree curve. Another one that we can show you here would be the knee with the 90-degree straight line with vanes. Look how the existence of the vanes will greatly reduce the average loss coefficient, right? So I go from 1.1 coefficient to 0.4, less of half. So on a straight knee, my loss would be 9.75 times 0.40, going straight to millimeters. So let's put 0.12, which will give 9.75.4 times, which gave 0.47 millimeters of water column, which gave 0.47 water column. In a smooth branch, I'm calculating the coefficient here because here, this load coefficient is simply negligible. So let's go. If it were the loss, it would be 9.75 times 0.5 times 0.12. Again, to go to millimeters of water column, 9.755, 5 times 12 times loss, 0.59 millimeters of water column.
Ramificação.
And branching from a rectangular section to a circular section, you can use the same reasoning. So there's no point in us repeating the calculation. I'm going to make this sheet available to you that illustrates the average losses. And here. Now in the rectangular section, for the rectangular section, I would like to draw your attention to this entry angle here. This entry angle is most often not used because the engineer, the installation designer, already considers the loss of load as if it were a straight entry. But I wanted to draw your attention to the fact that, for example, if I have an angle here, here is at least 7.5 centimeter, and this angle here is around 15 degrees. My loss coefficient is 0.75.
75.
Now, if it's a straight duct taken straight here, the loss coefficient is more than double 1.6. What I'm presenting to you, it's an average coefficient because the machines in ASHRAE have, as I already said, more than 200 standards of singularities, and with the most diverse proportions of measurements between them. It is an extremely complex database and unfortunately is not available free of charge. So with this that I'm making available to you, you can make your calculations regarding most of the pipeline networks that you may encounter along the way. Okay? So that's what I had to show you today. And once again, I would like to remind you that if you like the video, give it a like and subscribe to the channel. If you have any questions or suggestions, send us a message and we will answer as many as we can. Big hug and see you next time.